It's getting late in the day. The capacitor, it's a DC circuit. The capacitors become open. So, no, I'm writing with white pen. That's what's wrong. Somehow that's become the default. The capacitors become open. And if the capacitors are open, then I can ignore this whole thing right here because it's not tied into the circuit. And I can ignore this whole branch of the circuit right here. Everything I've got for my DC circuit, oh, and this capacitor's open, so it goes away too. So my entire circuit consists of VDD, RD, a transistor, a gate resistor to ground, RG, and a DC current source to negative VSS. Oh, let me just do this. I know the voltage on this side of the current source is negative VSS. Do I know anything? Do I know that the voltage up there is also negative VSS? An ideal current source drops whatever voltage it needs to keep the current constant. You have no information about what VS is based upon that current source. You don't know how many people I've seen do that on an exam. Just call. It's the power supply at the source. It's the negative power supply for the chip. Okay, so that is the DC equivalent circuit. That's pretty much it. If we know some more information about this, if we knew what I was, we also have I going through here, would be that information. If we know I, we know VGS, we know, oh, the other thing we know here too, we know VG equals 0, because no gate current. That resistor has no current going through it, so it's basically no voltage drop to ground. Once I get VGS, then I could figure out what VS is.
I don't like it.
Why not? What? Okay.
So this is the DC bias equivalent.
This is the DC bias equivalent. Why do I have that gate resistor there if no current's flowing through it? If we draw the AC circuit, which I hope is next, yeah, we're going to take the same circuit and draw the AC equivalent. So AC, the capacitors are shorts. So I just short them out. That's a short to ground. My DC voltage sources get shorted out. So this becomes a short to ground. And my AC current source goes open. I mean, my DC current source goes open. And so basically what I have here, the equivalent circuit looks like this. I have my transistor. I've got RD to ground, and I also have RL to ground. So it's RD in parallel with RL on the drain. On the gate, now we see the purpose. We have V-sig, R-sig, and I've got RG tied into the gate, and the source is shorted to ground. There's the AC equivalent circuit. I could replace that with a small signal equivalent model. Sometimes this helps you to do this. But the small signal equivalent model is I have little v, little g, little s on the gate. I have the drain up here. The drain has that dependent current source, GM, VGS. There's little RO in there. And I have the source down here. If I look at the AC thing I've got up here, my source is grounded. So I just ground my source. My gate sees a voltage divider. Sorry, this is sloppy. RG. And this is grounded. And my drain sees the parallel combination of RD and RL. No, please. RD over RL. So that would be a circuit you could analyze. You've got a voltage divider on the input. You have a current source going in the parallel combination of R0, RD, and RL.
So on the top one, did you just, that's an equivalent circuit listed?
Yes, I did, because see, RD's going from this point to ground, and RL is going from this point to ground. So I just kind of avoided drawing a second resistor by just saying it's the parallel combination. Okay.
So we have the dependent current source.
Yeah, this is right here, this piece of it is the small signal model of the transistor. This is the one we've been using. And all I did is I replaced the transistor with that small signal model. The one on the bottom is the one you would use if you really wanted to do the circuit analysis.
This GMVGS, is that in terms of amps? Current source?
It's a dependent current source, so it would have to be, the units would have to be amps per volts, which is either ohms or 1 over ohms. Amps. V equals IR. It would be 1 over ohms. It's, yeah, you're right. It's a conductance. It's a transconductance is the name of GM. It's a transconductance parameter. Okay. Frequency response. We will get to this in more detail, way more detail, after exam 2. For right now, what we're doing is everything we've been calculating, the voltage gain, the input resistance, and the output resistance are these mid-band values. When we look at this in more detail, we're going to find things like those decoupling capacitors like CC1 and CC2 that I said were infinite, actually cause the gain to roll off at low frequencies. Those are desirable. They're DC blocking. They help us. The real problem with MOSFETs is the internal capacitances of the MOSFET cause the frequency to roll off at higher gains. So they have a limit to how fast you can run a MOSFET. And it's limited more by something called the Miller effect that we'll get to later after Dr. Cambo comes. And talks about the Miller effect a little bit. But the Miller effect limits the bandwidth in a common source amplifier. So the common source amplifier actually is one of the slowest ones. And MOSFETs in general aren't very good for frequency response. As they get smaller, it improves a little bit, but that had the speed of the MOSFETs has not been going up as fast as the size has been going down. It was a big area of research in the late 80s and the early 90s, and they kind of hit a wall and have gotten stuck there. The alternative, if I really need the high frequency response, is to go to BJTs, go to different types of amplifier circuits. Yeah. This is a common source amplifier. And we've been through this. I don't want to do this again. We're running out of time. I want to do more of these circuits. So this one right here, my input is on the source, my output's on the drain. It must be a common gate. If I want to draw the AC circuit for that, I'm going to do the same thing. I'm going to short out the capacitors. I'm going to ground the DC voltage sources. And this is a signal voltage, so that's an AC. And I'm going to open up this one. So if I want to draw the small signal model of this, I've already got a sketch of it over there, so I'm going to bypass that first step. I've got VGS, got the source, I've got the gate, I've got the drain. This is GM-VGS, and this is little RO. So the source of this is going, well, that's the current source is open, is going to R-sig to V-sig. The gate's going to ground, and the drain is seeing the parallel combination of RD and RL. So again, once you're able to draw those circuits, you can either do the circuit analysis by hand, which is some people's lazy way, or you can do it my lazy way, which if I look at it and I'm stumped as I plug it in, I plug this model into multisim, and I figure out what I wanted to know. And then I kind of check it against reality. If I get like a huge gain through a common gate amplifier, I'm going to be surprised and fix my circuit. Okay, so this is a inputs on the gate, outputs on the source. This is a common drain. We can do the same thing here. It's the same process. I'm drawing the AC circuit, small signal and AC is the same thing. I short out the capacitors. I put my DC sources to ground, and I open up my current sources. So I start out over here, my gate, plus minus VGS. You get to do this on the next homework, and I'm sorry about that. Homework 7's bad. I gave you extra day for it.
Does negative VSS also go to ground because it's marked as a source, or?
Yeah, it would, but it's a ground. It's a ground on the other side of an open circuit, so it doesn't really matter.
Okay.
Yeah. GM, VGS, RO. The drain on this is grounded. The source is going to RL. And the gate sees a voltage divider. R-sig and RG. Okay. I got 5 more minutes. Okay. Let me see where I'm going with this. Let me use the most of my 5 minutes. We did that already. I think we've done that one, or we've done something similar to that already. This is the best use. Well, I think have we done this one already?
Yep, we did that one too.
Okay, we've done this one already too. So any questions? Homework in the universe or anything? Homework 6 is a little rough. Homework 7's a little rough. Homework 8, you read the papers and you answer the questions. So it's not so bad. And that's, yeah. And exam 2 is a little bit tougher than exam 1, mainly because you have to do some circuit analysis. And when I say circuit analysis, I mean Ohm's law. Yeah, it's the 188 stuff that bites everybody. The people who pass the exam usually get at least the 188 stuff right. And then once you apply the 188 stuff, the saturation current equation will get you far. Jordan, are you here? Jordan Beverly. Okay. Once you apply that saturation current equation, you write all that down on the schematic, you can find like the DC values fairly easily. There are current mirrors on there. There are Cascodes and things like that. We'll get to.
So is this what lab 4 is going to be about? We're going to be trying to like design a specific circuit to these specifications?
No, there's no analog in the lab.
Oh,
Okay. The analog in the lab is measuring timing delays on digital circuits. What we do in lab 4. The first week, we look at layouts. We look at the layout of a simple digital circuit. And there's a bunch of readings to do in the lab 4 folder that tell you that, okay, basically what all the different colors on the layout represent different layers. And in the drawings, it shows you kind of like what order the layers are in the cross section. So given this top view picture of the circuit, you have to like do the side view version of it based upon, okay, I've got pink here, so that's poly. So poly's on this layer relative to this layer. So you basically drawing the cross sections. That's week 1. Week 2, you're given 4 different schematics. No, you're given 4 different layouts. And you have to draw the schematic in Pixis based upon what the layout looks like, including the sizes of the transistors. So you have to look at the transistors as they're laid out and figure out what their sizes are. There's a little ruler tool you can do that with. Weeks 3 and 4, you're given the schematic of a buffer. And please thank Sean Robbins if you see him when we get to this part. You're given the schematic of a buffer. And you're given a long-winded, not quite accurate version of how to lay out the buffer from the schematic. Okay. Last semester, Sean went through and corrected most of that. It was something that Mentor Graphics had online that we downloaded basically on how to do this. And there was many things on there that just plain just didn't work. And we had the legend and the verbal history, so we'd help people as they went along. Sean went through and rewrote it, so it's much more clearly. It's the Pixis. Well, I'll point it out to you when you get in lab, but it's the one that ends in SMR. There's one that's like Pixis SPT something or other, layout directions. There's another version in there that says corrections, which are correct or not the whole thing, it's just corrections to the original one. And Sean took it and put it all together and updated it last semester. So I'm hoping the lab, that part of the lab goes much more smoothly. Other than, be careful when you get to the layout part, follow the directions closely, because if you mess something up, there's some things I know people typically mess up, I'll warn you about, like don't delete the pen. But if you don't follow the directions, sometimes the only thing you can do is start over, which is why this is 2 weeks of the lab. The first semester I taught this course, I gave bonus points to the one person who finished it. And we were getting a better track record. There's actually a smiley face at the end. You'll see it. Okay. Time to go. Yeah. Figure out what. We're meeting in person for the first time since June. That's why I was excited. I wanted to read it, but it's 12 paragraphs long, probably a bunch of rules. Okay. Okay, sure. Okay. I'm just going to close.